So hello everybody. Welcome to our next session in the IP Showcase. And I'm here with Jed Deame, who is CTO of Nextera Video. And he's going to be giving us a tutorial on the NMOS protocol. So I'm very much looking forward to this. Take it away, Jed.
Thank you, Wes. Good to be here today. Thank you all for showing up. So I'm Jed with Nextera Video. What we do is we help manufacturers add 2110 and NMOS capabilities to their products with FPGA cores, software, etc., and design services as needed. So today I'm going to walk you through what the heck is this NMOS thing I've been hearing about. Explain it to me like I'm a 5-year-old so that I can really understand it. So this is going to be a low tech, but really walk through the functionality. What does this thing do? Why is it important? This is the long list of things we're going to go through. I won't read through them right now, but this is the index you can refer back to if you're looking at this online. So let's start out with, what is NMOS? Well, it stands for Network Media Open Specification. It was developed by a group called the Advanced Media Workflow Association, also known as AMWA. And it's delivered slightly different than SMPTE specifications. It's more of a software flow online set of specifications. They're not true standards, but they are specifications that are agile and keep up with the needs of the industry very quickly, so we can move quickly and get products out there very quickly with a reasonable amount of oversight and versioning and all that you would expect. So what does it do? It enables plug-and-play connectivity in an IP world. So just like we had an SDI, you could go to a router panel and hit destination take source. NMOS is what allows IP devices to do that same thing in a nutshell. So plug and play and push button routing. How exactly does it do all that? Well, there are a couple additional components. There's this registry that's kind of a new thing we didn't have in the SDI space, and that's what gives us our plug and play. So when you turn on your SDI devices, they're just sending a stream, you don't know anything about it. But you turn on an IP device with NMOS, whether it's a camera or a monitor, they go tell this registry, hey, I'm a camera, this is my vendor ID, these are my capabilities, here's my IP address. So it's all there in one nice, convenient place. And then a control panel, which by the way, these are the exact same control panels that worked for SDI, with a little bit of software change, can now go read this and read the registry and say, oh, well, I've got 2 cameras on my network, I've got a display on my network. It can actually populate that in the control panel. So that's the plug and play part. And then you do your destination source take, and you've now connected. The way you do it is actually by sending an IGMP join message to the switch. This stands for Internet Group Management Protocol. So that's the way we switch an IP. Instead of having a big cross-point matrix like a SDI router, we're actually telling the switch, stop sending this current stream that I'm now subscribed to, and now subscribe me to the new switch. Because an IP, all the streams are blasting into the switch and they're held there until somebody asks for them. So how is NMOS accessed? How do I talk to this from another control system? Well, the software guys will say, oh, well, it's easy. It's through this RESTful API. Well, what does that mean? Well, it's really just an HTTP endpoint. It's just like your browser. You can type in HTTP and apple.com or google.com. If you put in the actual IP address of the device you want to talk to with this x-NMOS, it shows up as a file system inside of each device. So all the parameters of the device, all the network configurations, all the things you might want to read or all the things you might want to write are now just mapped into this kind of web-friendly interface. So it's very easy for external systems to interface with it. There's a few examples there you can look at. So what are the interfaces and how does this all work in an actual NMOS node? So here's your controller, which we talked a little bit about. He's the one that's doing these takes. This big box in the blue would be like a node, which could be a gateway, maybe something that converts SDI to IP 2110. The controller would send these HTTP transactions, these puts and gets. It goes to this thing called this node API, which are really just different paths, just different folder structures within this HTTP infrastructure. And then the control logic, which is your NMOS software core, that catches those and then tells the hardware what to do, programs it with the addresses that you need, et cetera. and that turns on the streams, which is over on the far right. The transport can then be enabled or disabled depending on whether it's an encoder or a decoder. And at the far right is the PTP Grandmaster interface that allows all these devices to be kept in sync. So there's a few required components for NMOS. Required by who is the question? Well, the EBU actually mandated a few of these in this technical document 3371, which is the minimum requirements to build and manage IP-based facilities. So there are a few of them listed here, ISO 4, 5, 7, 8. We'll go through these individually and let you know what they are and how they work. So first, the simplest one is ISO 4. This is our registration and discovery API. This is what gives us the plug and play. There's what's called a node API that your device, your node would talk to, whether it's a camera or a monitor, and he would provide that so that other people can access him in a standardized way. And then you've got your registration API and query API. These are part of that registry, that new device that we talked about a minute ago, that is the kind of the index of all the devices on your network. Next we have ISO 5, which is the connection management. This is what does the switch. I want to connect device A to device B. It's an ISO 5 message that does that. And we call that an activation in NMOS ease. And there's three types of activations you can do. You can do an immediate activation, which says now connect A to B. You can do an activation that's relative, that says in 5 seconds connect A to B. Or you can do an absolute activation that says at 12 p.m. let's connect device A to device B. So very flexible, very powerful. Next we've got ISO 7. So this is useful not in every particular device. A gateway might necessarily not need it. But if you're a production switcher, vision mixer, or you're a multi-viewer, or you're a camera, something that wants tally information, any type of real-time information that needs to be sent from A to B would use ISO 7. And this is a detailed diagram, which I won't go through right now in the interest of time, but it sends information like if you hit a program button, if you hit a take on a production switcher, you can light the tally light on the camera using this ISO 7 technique. Next we have audio mapping. So in SDI we had convenient ways to de-embed and re-embed audio and shuffle it, but you actually had to buy hardware for it, so it was a little bit cumbersome. In IP, in 2110, remember we're sending video, audio, and ancillary as 3 separate streams. So you've got all these audio streams already floating out there. Wouldn't it be nice to be able to mix them and mux them and map them together? Well, ISO 8 specifies exactly how you do that through this API that specifies the I/O and the map. An example of how this mapping is done, we actually did it 3 years ago. Last time we were here at NAB, we did an audio demo that showed how this ISO 8 mapping worked. We had a couple different vendor products, a couple senders, and some receivers, and we used this NMOS GUI here to connect them together. So if you look on the left side, we actually have 2 different streams. Stream 1, which has channels 1 through 8, Stream 2 that has channels 1 through 8, and then our output, if this is, let's say, a gateway converting IP to SDI, those would be the 16 audio channels. So you can subscribe to multiple IP streams and pick and choose which channels you want and embed them anywhere you want in your SDI stream. So it's a nice kind of free thing you get with no additional hardware. You can just map what audio channels you want to pick off of different audio streams that are out there on the network, embed them into a single, could be an SDI out or could be another IP stream. And here's what that looked like in the demo. We had their 3 sources, and in the particular example, the harmonic processor was sending this kind of ramp audio stream in the upper left, and we were receiving it with the Nextera gateway at the bottom where we inverted the channels. Okay, the next thing we have is called ISO 9. That's the system resource, and that solves a couple problems that we have in global configuration. How do all these devices, they're all intended to work together in a broadcast environment. How do they know, like, well, what's my PTP domain and my announce interval and what version of NMOS am I running? Instead of having to go in and manually type those in every box and every control system, there's one central resource that publishes this information using DNS service discovery, DNS SD. So all these kinds of information that I have listed here, as well as there's a system ID that is unique to every system. And that's kind of neat, so when a piece of equipment wakes up, he can look at that system ID and see, is that the same system ID I saw last time I went to sleep? If so, wake up in the exact same state, right? If I was transmitting, I want to be transmitting again. If it's something different, oh, somebody must have moved me from system A to system B, so let's turn off the transmitters, maybe go to a default state. So next we have the optional components. One of these is called ISO 6. That's a way of doing software-defined networking. I mentioned IGMP a minute ago. This is an alternative that's a layer between the switch and the broadcast controller called this Network Control API that lets the control system talk directly to the switch and have the switch manage that, the connections. It's got a couple benefits. You can do things like network topology, discovery. You can authorize connections. You can manage your bandwidth. So it's used in some cases. I'll show you exactly how it works. So you remember in the IGMP system, the receiver would send this IGMP join message to the switch. That cloud is the switch, and it would say, you know, disconnect me from this stream, connect to this stream. And that actually works really well, and there were some tests done by Sony and others that showed this would work for thousands of devices. So most people are doing it this way, but if you want a little more control, you can do this software-defined networking approach where it's actually the control panel sends this ISO 6 message to the switch and tells it directly, hey, disconnect this guy and connect this guy. So different way of doing it requires switches that have that support and control systems that have that support. Next, we have a couple things called best practices, best current practices. BCP 002 is the first one I'll talk about. This is grouping. So I mentioned a minute ago that audio, video, and ancillary are sent as 3 separate streams. Well, you might want to know which 3 streams go together if they're all coming from a playout server, for instance. So this is a mechanism within NMOS that allows us to tag these different streams and say they're coming from the same source. You can add tags that are called group hints. You can also add roles, for instance. Here's an example. If you had a playout server with a video, audio, and ancillary stream, video and 2 audios with it, you could tag them all as playout master. So these 3 different streams have the same tag, so your controller would know. So if you're doing a route from A to B, it would move all 3 of those. But there are some differences. You want to know the roles of each of those. So the video role is, in this case, the primary. But you've got the 2 audio streams. One, in this case, is a 2-channel stream, and the other is a 5.1. So it just adds a little more usability to the system so that an operator can see what's going on and kind of manage this. It adds a little more to the plug-and-play capability of NMOS. Next big topic is security. So a lot of broadcasters are really screaming for this. They're very conscious about having secure systems, keeping bad actors from getting in and doing things they don't want. It can be very costly. So in the NMOS committee, when we looked at security, we had 4 major goals in mind. The first was confidentiality. Let's make sure that we're moving data from A to B and it's unreadable by third parties. Second is identification. We need to make sure we know who we're interacting with, that it's actually a trusted party that's sending us the information. Third is integrity. We want to make sure there's nobody tampering, no man-in-the-middle attack, somebody sneaking in and doing a switch or something that we don't want to do. And finally, authentication. Make sure that the packets are coming from the API that it's really interacting with. So how do we implement these? Well, we've written a couple of these BCPs to describe ways of implementing security, BCP 1, 2, and 3. The first one's pretty straightforward. It says use TLS. Well, what does that mean? That's this transport layer security. So instead of an HTTP put or get, you use HTTPS, like you see most of your web browsers now default to HTTPS. So that actually encrypts the data. That's what that S means. You're actually running an encryption on that command message from A to B, and anybody that looks at it in the middle is just going to see garbage. The second is 003-02, which is authorization and user management. And then finally, we have 003-03, which is a way of provisioning certificates in the system, these security certificates, so that we know that we're talking to trusted sources. Part of this security effort resulted in another IS standard called IS-10. It's the authorization API that goes along with the BCP 00302. It uses JSON web tokens and a very common authorization system called OAuth 2.0 that's used heavily in IT-based systems. So how does this encryption and decryption system work? Well, it's pretty simple from the high level. It uses this, what's called a PKI or public key infrastructure. And the idea is that the sender has this key, Alice in this case, has the receiver has a key, a public key, and she gives that to Bob, who wants to send a message. So Bob says, all right, I'm going to send you this message that says, hello, Alice. I'm going to encrypt it with your public key that's openly available, and she can email it to him. And that now creates this cipher data. So it's all encrypted at that point, but in order for anyone to decrypt it, you would need the private key. So if Alice is the only one that owns her private key, she's the only one that can decrypt that message. So pretty simple way of sending secure data back and forth. There's lots of techniques of creating these keys and sharing these keys and distributing these keys, and that's what part of this standard talks about. So how does this work in a real broadcast system? Okay, really interesting. We added security. Well, I still want to switch A to B, but I want it to be secure. Well, you've got your source and your destination. The broadcast controller we talked about, that's the same button panel that now speaks NMOS. Well, we've added this one new component. It's an authorization server, which is really nothing more than a piece of software that's running on some PC on your network. So I want to do a connection, so I go and I push something in my button panel, source, destination source take. The broadcast controller, before it talks to the source, the destination, it sends this request to the authorization server using this OAuth format. And it says, hey, I want to do this. Is this approved? Right here are the credentials of the user that wants to do it. Is he approved to do this? And he comes back and goes, oh, yes, he is approved. Here's a token, this JWT token that it sends. The broadcast controller sends now this switch, or what we call activation, to the source. And the source says, well, wait a minute, let me check that JWT, see if it's valid. I'll check it with the public key of the authorization server. Great, that's good, I'll start transmitting my stream. Now, the receiver has to listen to that stream, he has to subscribe to it, so we send an activation to him, and then, well, he's got to do the same thing and validate against the public key. And once all that's set and validated, now we have a stream flowing from A to B. So nice, secure solution to make sure that no bad actors get in and interfere with our streams. So that's kind of the overview of here's what's required in NMOS. Here are some of the optional pieces that are rolling out very soon that are all fully standardized, ready to go. They've been interop tested, and different developers are in different stages of implementation. What's next in NMOS? Where do we go from here? So we'll talk a little bit about future development. First, we have this thing called BCP 006, which is how do we use NMOS if we have a compressed environment. So some of you have probably seen JPEG XS is one of the leading compression contenders for moving high bandwidth data over smaller networks. A lot of these newer things, by the way, are intended to help get into the Pro AV space and push this 21 technology into broader markets. So this is a set of standards that talks about how NMOS can work in this network, and it's just a few additions, a few technical things. It says, well, let's use ISO 4 registration and discovery, and let's use ISO 5 switching. Let's just identify our stream as this video/JSXV so that the receiver knows what it's getting, and we'll make some updates to the SDP file. The next thing we want to do, especially in Pro AV environments, is we want to know who we're talking to. We want to make sure that we have compatibility between the sender and the receiver. What if, now you bring PCs in the mix, the PC could be outputting 1600 by 1200, right? And your receiver is an SDI style monitor that only knows broadcast formats. Is there a compatibility? Well, it'd be nice if the controller could tell you, yes, you can make that connection, or no, you can't make that connection. So that's one of these things. It's kind of like what EDID does in the HDMI world, is it sends a list of known formats that the receiver can support and make sure that the sender, or at least the control system, knows about those. So you can either alert the user that it's incompatible and it won't work, or in some environments, maybe in a Pro AV or boardroom environment, you want to force it to work. So one example would be, you've got a sender, you've got a receiver that could support both 4K or 1080p. The sender, it would be set to 4K, which is the highest resolution it can handle. That's all great. So now you're talking 4K sender to 4K receiver, but now another receiver hops in and goes, well, I want to listen to that stream too, and I don't want to make you put out 2 streams, but I can only support 1080p. So the controller could be smart enough if you put it in this mode and say, well, all right, I know I've got one guy that wants 4K, one that wants 1080p. They can only handle 1080p, so I'll just lower my resolution of my sender so both guys can connect. So it would be something you would turn on or off as needed. There's some other supporting BCPs that go along with that help bring in EDID capabilities from HDMI devices and map those into NMOS so that everybody knows what's going on. Then, this is kind of the granddaddy of them all, device control. What if NMOS was not just used for switching and registration and discovery? You know, it's already announcing itself to a registry. It's already got these great interfaces. What if we could do device control, right? I want to set up some of my parameters. I want to do some moding of my device. Why have 2 separate APIs, NMOS for switching and another vendor-specific one? Wouldn't it be nice if I could talk to gateway from vendor A, B, C and send them the same command set and do the same thing? So this is a pretty lofty goal, and there's been a lot of work. There's big modeling effort built on top of this, but the goal is to really create this universal control protocol, expose this common API that's extendable by the vendor. But if you got a common set of features, let's use the same name for those, for God's sakes. Let's not try to reinvent the wheel 30 times, but let the vendor extend it as needed. And this could be a replacement for SNMP, which has some limitations. It's difficult to implement, for OpenConfig, which looks very promising, but it's a little narrow in scope, or Ember Plus, which is great, but still not really 100% open. So if we can build these models and create the structured view for control and statuses inside our devices, that could be really powerful. So the intent is to use current technologies that are already used in NMOS, like WebSockets and the JSON, which is the text-based command formats. And we've got some of these MS specs that talk about the frameworks and the block specs. All this is available on the AMWA wikis. You just Google AMWA wiki if you want to get more information about this. So our takeaways are NMOS, ISO 4 and 05 are solid, stable, mature. They have been for 3 years. They've been working great. They're at the node level. They're doing exactly what they need to do. They're employed in just about every new product that's out there is going to have an NMOS controller in the node. There's some new features that we talked about, ISO 8 audio mapping, system discovery, BCP 002 grouping. Most of those have been adopted by now. And then the security piece, which is really going to take it to a new level of authentication, a new level of functionality. That's just beginning to roll. So finally, NMOS does enable plug-and-play switching of IP devices and can be extended to go far beyond that for device control. That is it. Thank you very much for your time.
Thank you, Jed. That's very good. Thanks a lot, Jed.